Wow, it's packed in here. I'm humbled. Well, thank you all for coming in and choosing to spend this 1 hour with us in this busy week of reInvent. We hope you will learn something new. Welcome to our session, Build a Data Foundation to Fuel Generative AI. My name is Vijeta Chakraborty. I'm a senior manager with Amazon S3, and then joined with me today is Jordan Dolman, a principal product manager with Amazon FSx. It's no surprise that generative AI is transforming virtually every industry. It's more and more capable today of generating new content, whether that's text, audio, and video. For example, we have healthcare customers that are generating personalized treatment plans by analyzing patient records. We also have automotive customers that are innovating in engineering and design by generating new concepts. What we know to be true is that data is really the heart of generative AI. It's what's differentiating your applications as well as speeding up innovation in your organization. So the purpose of our session today is to walk you through how some of our customers are preparing to build with generative AI. The most common questions that we get from customers is, how should I think about foundation models? What sort of data considerations do I need to keep in mind? And what sort of a storage infrastructure do I need to support all of this? Let's first start talking about foundation models. Now, on a very high level, there's really two things you can do. One is you can reuse an existing foundation model, or you can choose to train a new one. There's a few different approaches when you choose to reuse an existing foundation model. And we want to talk about the first and the simplest approach, which is Retrieval Augmented Generation, or RAG. Now, with RAG, you're using your organizational data to customize the model's output without needing to retrain it. Here's what RAG looks like broken down. First step for you is going to be that you're going to want to create a library of information with your organization's data that you want to send to structure the foundation model. Now, you've got that library created, and a user asks a query. Now, you'll send this library to structure the output of the foundation model. This entire exercise is called prompting. In fact, prompt is a set of curated text or instructions that is used to guide the model in providing a more appropriate or relevant response. Now, in AWS, you have all the tooling you need to build out your RAG workflows. For example, with Amazon Bedrock, you're able to create a knowledge base with your organizational data in an Amazon S3 bucket or other data sources. Amazon Bedrock also gives you access to a ton of foundation models, for example, Amazon's Titan and Anthropic Claude. Here's an example of one of our customers using RAG in their organization. Now, we've all heard of Pinterest. Pinterest is a visual inspiration platform, and they have one of the largest data lakes in S3. It's almost 1 exabyte wide. Now, the goal for Pinterest was to use large language models as well as their existing data within S3 to improve their analytics productivity. Now, on any given day, their data engineers have many different questions that they need to answer. Pinterest wanted to take these questions, these are text-based questions, and convert them into SQL-based queries. So with the help of large language models and this RAG workflow on their existing data in S3, they built out query tools that were able to convert text-based questions into SQL queries. And these query tools improved the productivity of their data engineers by almost 40%. Coming back to this slide and talking about another approach of reusing an existing foundation model, we're going to talk about fine-tuning. It's a little bit more complex than RAG. Now, with fine-tuning, you're adapting the model to perform special tasks that were not covered in the pre-training process. This reduces training time, improves model accuracy, and allows for customization. With fine-tuning, you're using your enterprise data, your domain-specific enterprise data, to basically adapt the model or customize it for performing special tasks. You're only doing it when you need to extend the specialized knowledge of the model, for example. So here's an example. Let's say you're developing a medical diagnosis model. Fine-tuning an existing foundation model on a highly curated set of medical records will really yield appropriate and accurate responses. Again, as you can imagine, AWS has all the tooling you need for fine-tuning. For example, you have Amazon Bedrock as well as Amazon SageMaker Canvas. You will need access to high-quality and labeled data for fine-tuning. You want to have access to foundation models, and SageMaker gives you the option to experiment with the model's hyperparameters, for example, learning rate and batch size. That way you can customize the fine-tuning process for your specific data, as well as the outcome that you're looking for. Here's an example of a customer using fine-tuning, and that's my personal favorite now that we're in the December month of the year, Booking.com. So what Booking.com wanted to do is they wanted to build an AI trip planner that provides personalized recommendations to customers in a very conversational manner. They tried doing this, but they had several different latency, data, as well as infrastructure challenges in generating these type of recommendations. Now, Booking.com is sitting on years' worth of booking reviews, customer reviews. That's their most valuable data set. What they did is they enhanced a RAG workflow on top of this data set of booking reviews to generate highly personalized trip recommendations. They didn't stop there. They fine-tuned an existing foundation model, Llama 2 in this case, to create an intent detection model with 7 billion parameters. Now, with this intent detection model, as well as the enhanced RAG on their booking reviews, they were able to create the AI trip planner that they wanted that provides highly personalized recommendations in a very conversational manner to customers. Coming back to the slide, one final time, we want to talk about continued pre-training as well as training a new model. Now, if you're considering these two approaches, you probably have not found the output you want from RAG or fine-tuning. With continued pre-training, you're really picking up where the model provider left off. And you're using your enterprise's data to not only extend the specialized knowledge, but also the generalized knowledge of the model. Training a new model, exactly what it says, you're training a model from scratch. Now, you're only wanting to do this if the model that you're looking for does not exist yet. Both continued pre-training and training a new model are very resource intensive, and they also require specialized skills. However, the model accuracy that you get, as well as relevance, is much superior to the previous two methods, RAG and fine-tuning. Especially if you're training a new foundation model, you need access to a large corpus of data. You need specialized skills as well as specialized infrastructure. Now, in AWS, you have Amazon SageMaker, as well as access to GPU instances. You also have access to specialized storage offerings like Amazon FSx for Lustre, in addition to Amazon S3. Excuse me. Here's an example of a customer training their own model. LG AI Research is the research hub of LG. Now, they wanted to create a foundation model that is able to mimic a human brain. It has an advanced capacity to learn and has good judgment. Now, we all know no such model exists yet. So they decided to create their own. Now, within 1 year of using Amazon SageMaker as well as Amazon FSx for Lustre, they were able to create their foundation model called Xion. Xion is a 300 billion parameter multimodal model that's trained on image as well as text data. It is exactly able to mimic how a human thinks. It's able to learn as well as take action on its own. Now, previously, LG AI Research did consider making all of this on-prem. However, there were a number of challenges, including cost. That's when they decided that Amazon SageMaker is the perfect fit for their project. As you can see, in that architecture, they're using Amazon FSx for Lustre to load the data from their Amazon S3 bucket into their GPU instances. And then you can see from the top right that when those GPU instances are training, they're also spitting out checkpoints as well as model artifacts, which LG AI Research is then archiving to a different Amazon S3 bucket on the top right. So we touched upon few different ways on how to use or reuse an existing foundation model as well as training a new one. Now, let's talk briefly about the data considerations that you need to keep in mind for all of these different approaches. Namely, we'll talk about data discovery, data preparation, and data governance. First off, in the data discovery process, you want to identify your data sources and data formats. Let's start with data sources first. Now, there's plenty of different data sources when you're talking about generative AI applications. In addition to internal data sources like your internal wikis, company documents, support logs, and ticket information, you may want to consider using public data sets. Now, these public data sets could be academic, or they could be web crawl data, like the Common Crawl database that a lot of our customers will use for training new models. You may also consider purchasing data from a licensed content generator like Shutterstock or Bloomberg for financial-related matters. Once you've thought through the data sources, you want to then consider the data formats at play. Again, we see various different data formats, and those formats can really differ by the model that you're using underneath, as well as the outcome that you're trying to drive. In S3, we see a lot of structured data, specifically Parquet files. In fact, Parquet is one of the fastest growing data formats in S3 due to its superior query performance. We also do see a lot of unstructured data. Today, unstructured data formats like audio, text, images, PDFs are overwhelmingly dominating the generative AI workload. Once you've considered the data sources and data formats, we want you to assimilate all of this data and bring it into an Amazon S3 data lake. But first, the one consideration to have in mind is whether you want to load this data in batches or in real time. You want to load this data in a batch mode if the data is changing infrequently. For example, it's historical records, it's product documentation. You may also want to consider loading the data in batches if there's heavy pre-processing that's required. For example, you're tokenizing the data or creating embedding in the backend, storing it in a vector DB, and all of that. Now, there's a few different examples that AWS provides for loading the data in S3 in batches. For example, you have AWS CLI or SDK. You have transfer family to move files in and out of AWS. You have data sync to move data from on-prem to S3, as well as AWS glue crawlers that are automatically able to discover and catalog data from different sources and load it into S3. The other option for you is to load data in real time. So you're really wanting to load data in real time when this data is changing frequently. For example, it's live customer support, as well as social media, for example. Consider using the Amazon Kinesis family of services to load data in real time, because then it's able to collect, analyze, and process the data in real time, as well as load it into an Amazon S3 bucket. What we see across the board is that for RAG workflows, customers generally prefer the batch loading of data. It's much simpler to implement, as well as more cost-effective. So you've brought all of that data into an Amazon S3 bucket. What's next? Now you want to be adding relevant metadata to enrich this data. And again, there's various different methods to do that. For example, in RAG workflows, descriptive metadata like titles, summaries, as well as categories are very, very efficient for retrieval type of workflows. However, for fine-tuning or pre-training, you want more extensive annotation. For example, customers will use an instruction response format, or a question-answer format, or a sentiment analysis format. Because with those formats, you're not only teaching the model how to interpret a specific sentence, you're also teaching the model how to interpret similar such sentences. A lot of our customers will use large language models as well as Amazon SageMaker to do this type of data classification and labeling. Now, you've added this metadata to your data, but how do you store it? Again, AWS provides a number of different options. First off, S3 has S3 object tags, a native capability through which you could add user-defined metadata on your data in S3. Customers will sometimes store this metadata in line with the data in the Amazon S3 bucket. And then a lot of our customers will choose to have their own metadata store, which is, let's say, a DynamoDB table or a Redshift table or an Iceberg table for better query performance. Now let's talk about data preparation. All of that data that you have in Amazon S3 bucket may or may not be ready to be consumed by foundation models. We need to prepare it in the background. Again, the data preparation can vary a lot by the data format that you have in your Amazon S3 bucket. Here, we'll walk through an example of what data preparation looks like for textual data. So starting out on the left, you want to first identify your data source. So you're either bringing in new data or you're starting from an existing data lake within S3. You're taking this large data sets or documents and breaking it up into smaller chunks of text or tokens. These tokens are more easily consumed by computers. Then you're breaking up these chunks of text into a series of numbers that we call embeddings for, again, more easily that are more easily consumed by computers and well understood. Once you have those embeddings, you're storing them in a vector DB or a vector store like OpenSearch. These vector databases are very efficient in similarity searches. They have specialized indexing system that helps you for these type of retrieval workflows. We talked about breaking the text into smaller chunks of text. We call this process tokenization. In fact, the goal of a token is that these are small enough that they can be quickly processed by a computer, but they're still large enough to retain context and meaning. Now, up here is an example of us breaking up a shareholder letter into smaller chunks of text or tokens. Now, a token is not exactly a word. Sometimes a phrase can be a single token. Sometimes one word can be several different tokens. The rule of thumb is that 700-ish words will get you to about 1,000 tokens. But again, that can vary based on the model that you're using underneath. We also talked a little bit about vector embeddings in the data preparation process. What are they? An embedding is nothing but a series of numbers in high-dimensional space that represent text, word, and phrases. They represent the meaning of that text as well as the relationship between two pieces of text. Let's look into an example. So here we have a database of movies. We've pulled up 3 examples of space-related movies: Inception, Space Odyssey, and Apollo 13. Now we're going to annotate that movie with several different things like title, release year, genre, director, and a brief summary. So for Inception, we have Inception released in 2010, sci-fi action, directed by Christopher Nolan, a thief with the rare ability to enter people's dreams and steal secrets, blah, blah, blah. From there, we choose an embedding model to create a series of numbers, which we call embeddings. For the purpose of this exercise, we're going to assume those numbers represent that piece of text that we just called out. Once you have those embeddings, you want to store it into a vector DB like OpenSearch. Now, once all of that is set up, let's say a user comes in and asks a question to the large language model: recommend me a movie about space and dreams. That user's query is again converted into embeddings. Your application is going into the vector DB and looking for the embedding that's closest to this user query. It retrieves that text that we talked about and then goes on and recommends the movie Inception to the user. Why? Because it is a movie about space and dreams. So we talked about data preparation a little bit. We talked about that data source, tokenizing the data, creating an embedding, and store it in a vector DB. Now, all of those different processes can seem a little bit cumbersome for anyone to try out, but they need not be. With Amazon Bedrock knowledge bases, all of that is fully managed for you. With Amazon Bedrock knowledge bases, you're able to securely connect foundation models to your own proprietary data sources like S3, and you're able to supplement your prompts with the right information to structure and guide the output of these foundation models. Now, briefly, let's talk about data governance. How should I think about data perimeter when it comes to generative AI applications? Well, for most of you in this room, I hope data perimeter is not a brand new concept. Data perimeter is nothing but a set of guardrails and permissions that you use to ensure that your trusted identities are accessing your trusted resources within your expected networks. Now, all of those things that you're doing for your business-critical applications, you want to extend that data perimeter to also include the inputs and outputs of your generative AI workloads. For example, your training data, logging of the model artifacts, checkpoints, all of it. Now, this is especially critical when customers are using public data sets, for example, from the internet, or purchasing data from licensed content generators. Most often, customers will actually copy this data from the content generator's S3 bucket to their own S3 bucket within their trusted network before sending it for training these models. Another thing to consider is expedition of this data. There's terms and conditions that you negotiated with the content generator. Sometimes it's as easy as setting up an S3 lifecycle expedition policy on your bucket to ensure that the data expires exactly when you want it to, and not a day late. And then once you have this data perimeter, you want to be able to audit this data through and through. Amazon Bedrock is really well integrated with AWS CloudTrail. And with that sort of integration, you're able to see when a model was invoked, which IP addresses was it invoked from, who, what, when, and all of those details. AWS CloudTrail gives you data as well as management events. So with data events, we're able to see who, what, when, access the underlying data in S3. With management events, you're able to see who invoked the model, when was retrieval done, and by whom. In general, if you're using Amazon S3 as your proprietary data source for knowledge bases, you're always getting unmatched and fine-grained audit, compliance, and security capabilities. So just to recap, we talked about a few different approaches in reusing foundation models as well as training a new one. We talked about a few different things from a data consideration perspective, data discovery, data preparation, as well as data governance. Now, for all of that to make sense, let's see a quick demo for RAG. So here in my demo, I'm creating an AI assistant that will recommend us re:Invent sessions to attend. Now, the role that I'm playing in this demo is I am an IT administrator who's specifically interested in networking topics. Now, what you'll see me do in this demo is that I create two very simple CSV files, one that contains all my re:Invent topics, remaining capacity of those topics, as well as the date on which it's being held. I have another CSV file which talks about the roles of people attending re:Invent and the topics that they're interested in. We'll load them into an Amazon S3 bucket, hook it up with a knowledge base in Bedrock. We'll do the tokenizing, we'll see the embeddings, and then finally we'll test this knowledge base with Amazon Bedrock and Amazon S3 using a large language model, Claude in our case, to see if it's able to recommend me the most appropriate or relevant re:Invent session. Let's see all of that play out. So here's the CSV that we talked about, which has the re:Invent sessions, remaining seats, date. We just picked 5. Here's another one, which has the roles of people attending and the topics that I'm interested in, IT admin, networking. Great. We load them into an Amazon S3 bucket. Now here we are on Amazon Bedrock. We're creating a knowledge base. There's a few different data sources that I wanted to show. We're going to choose Amazon S3. We're going to provide it the bucket ARN from the bucket that we just created with the 2 CSV files. There's a few different chunking and parsing configurations. Again, just showing you all of this, but we're just going to go with defaults for almost everything to keep it really simple. We'll hit next. Again, a few different options for choosing embedding models. We're going to go with Embed English by Cohere. And then for VectorDB, there's a few different options here. It either lets me create a new one or reuse my existing. Since I don't have an own, I'm going to choose to create my own, a new one. There you go. We hit next. We're going to review all of those settings that we just configured, and we're going to hit Create Knowledge Base. Now, that process can take typically a few minutes, so we're just going to skip to the end. And there we go. The knowledge base is created. There's my knowledge base. And then we're going to go test against it. So first off, we're going to choose a model to pick. We're going to choose Anthropic Claude's. And then this is interesting. So we're going to give Claude a system prompt where I tell Claude that she is an AI assistant that is going to recommend reinvent sessions with more than 0 remaining seats. I also tell her that I'm an IT administrator and the topics that I'm interested in. Hopefully, you're all able to read that. Perfect. So we've given Claude the system prompt. We also have her hooked up with the data in S3 as a knowledge base. And then we're going to test. With all of those inputs in, we're going to ask Claude to recommend me a reinvent session. And then there she is, retrieving information from the knowledge base that we just created. And there we go. So she's telling me, based on the available sessions and remaining seats, I should attend Design World Architect and Networks on AWS, which is going to be held on December 4th, and it has 15 seats available. Perfect. Exactly what I wanted. It also gives me a few more recommendations. It's sorted by the remaining seats. So simple example, but hopefully that tells you how easy it is to hook up the Amazon Bedrock knowledge base with your existing data in S3. Now let's have Jordan join us to talk about the storage infrastructure considerations for generative AI.
Thanks, Bajeta. So now let's focus on the different storage options that we have for Gen AI applications. At a high level, there's a few different ways to interact with storage. You've got block, object, and file interfaces. And within Amazon's storage portfolio, we have a few different services to work with. Amazon EBS is our elastic block storage. In a generative AI context, it's typically used to create boot volumes to support your GPU instances. Amazon S3 is our vast-scale object storage for unstructured data. It's going to be the focus of a lot of the session moving forward. It's also been, obviously, the focus of the session up until this point. And then we also have a number of file system offerings. Customers typically turn to file systems when they're looking for a hierarchical data structure, the ability to have file locking mechanisms, or integration with familiar tools and services. In the file portfolio, we have two main families of services. We've got Amazon FSx and Amazon EFS. Amazon FSx has file systems like Amazon FSx for Lustre, which is an offering that's specifically designed for high-performance computing and AI and ML workloads. We have OpenZFS and NetApp ONTAP as well that serve roles in this generative AI space, typically for hosting developer tools and applications. And then Amazon EFS is our fully serverless elastic file system offering. Typically in a generative AI context, we see customers using this for user shares or inference workloads. For the rest of this session, we're going to focus primarily on Amazon S3 and Amazon FSx for Lustre, since these are the dominant services used when training or supporting Gen AI applications. Now, the data access options I talked about before, block, object, and file, will certainly create kind of play a significant role in your choice of storage offerings. But there's also a number of other factors that might influence which storage service you use for a given application. The size of your data set might influence the amount of capacity you need the storage service to provide. It also might influence how quickly data needs to be able to move in and out of that storage service. That's the throughput capacity. The size of the actual files or the I/O requests can also play a role in which storage services might be most well suited for your workload. That's because if you're working with small files, the time it takes to retrieve a small file really depends on the latency profile of the storage service, and we'll talk about that in the slides ahead. Lastly, the access pattern of the workload is also going to drive which storage service you use for a particular application. That's how many I/O or TPS transactions you need to make per second, which is a factor of the type of workload you're running and the number of concurrent GPU or users that are actually requesting data from your storage service. Now, these three factors combined, the data set size, the file sizes, and the access patterns, they all combine to create the performance profile that you need for your workload. And performance is particularly important in Gen AI workloads because a lot of them depend on the ability to scale the compute resources, whether you're training or providing inference workloads. In all of those cases, you want to make sure that as your compute scales, your data access capabilities scale as well. If they don't, you end up with a storage bottleneck. And a storage bottleneck means your GPU resources are underutilized. It means your workload takes longer to complete. And ultimately, it costs more than it should to actually get the job done. So now let's focus on storage in the context of these different Gen AI approaches that Bajetta mentioned before. For RAG, fine-tuning, and continued pre-training, where you're building on an existing model, what we've found is this group of customers is actually looking at storage in the same way. They have the same subset of storage requirements. Specifically, customers who are using existing foundation models are looking for storage that offers cost-effective place to store their data for hot and cold data sets. They're looking for high-performance data retrieval and processing, and deep integration with AI and ML workflows. And as you've seen, a lot of these criteria are met with Amazon S3 quite well. For cost-effective storage, if you've used Amazon S3, if you've attended this conference before, you might be familiar with the fact that S3 has a wide variety of storage classes that are each cost optimized for different performance profiles. Amazon S3 Express One Zone, all the way on the left, is optimized for the lowest latency object storage that we have on AWS. And then the rest of the storage classes, from S3 Standard down to Glacier Deep Archive, provide tens of milliseconds or minutes to hours of access for different workload patterns. S3 Intelligent Tiering allows you to actually efficiently store your data across that spectrum from S3 Standard down to Glacier Deep Archive. And in a generative AI context, we found that data tiering is particularly important when you're building your workloads on existing foundation models. A couple of examples of why this is so important and how to think about this for the different approaches we've talked about so far. In RAG-based workloads, you want to make vast amounts of data available to these existing foundation models. You saw a demo just now where the model was able to access the knowledge base and pull out relevant content so it can be served up as a part of a response to the prompt. In this case, you want to make sure that those responses are very quickly returned from the storage service. And so S3 Standard, S3 Standard IA, and Glacier Instant Retrieval are all good storage classes to use for a RAG-based workload because they provide 10 millisecond access for RAG-based workloads. If you're doing fine-tuning or continued pre-training, you want to make sure that that data is actually an S3 Standard at the time of your training, because that's where you're going to get the best bang for your buck in terms of price and performance. But once the training workload is actually done, taking your labeled data that you used for fine-tuning or a corpus of data that you might have used for continued pre-training and tiering it down even to Glacier Deep Archive is a perfectly reasonable way to make sure you're optimizing your costs in the cloud. Another thing that we've heard our customers talk or ask us about is what's the best way to make sure that they're using their storage in the most cost-effective way? How do they find the data that's not going to be used, and how do they think about storage in that context? And we have storage services like Storage Lens that allow you to kind of look through and find ways to optimize your S3 data lakes. But quite frankly, one of the most cost-effective things you can do is work with S3 intelligent tiering to take a hands-off approach and let Amazon S3 actually automate a lot of that tiering on your behalf, find the data that you're not actively using, and move it into these storage classes for you. The next thing that our customers are telling us when building on existing foundation models is that they need high-performance data retrieval and processing. This is another area where Amazon S3 shines because it has the ability to support parallel access to many different requests within a given bucket. Now, in some cases, you might need to re-architect your data or plan where the data lives within your S3 data lake across multiple buckets in order to support the right level of performance from your workload. But generally speaking, S3 is designed for high levels of parallel access, and it can support all of the ingest, the pre-processing that we talked about for RAG just now, and then actually supporting the data access during your inference workloads as well. And then the last thing that customers are asking for when building on existing foundation models is integration with AI and ML workflows. We saw a demo showing how Amazon S3 integrates with Bedrock, and we talked about things like AWS Glue or using Amazon Athena to index and create data catalogs. So you can do some of those things quite well just with Amazon S3 out of the box. But there are also some workloads that really depend on file-based access. And Amazon S3, being an object store, doesn't always provide that native compatibility. This is where we've worked really hard over the last few years to make sure that Amazon S3 is compatible with the most popular workflows that our customers are asking us to help them with when they're building their generative AI applications. That means for Amazon SageMaker, we have file mode and fast file mode that allow you to load data directly from your S3 data lake into your GPU instances. It also means we launched the Amazon S3 connector for PyTorch, similarly to allow you to have a library that you can use that's optimized for Amazon S3, that uses multi-part downloads and uploads to move data back and forth when you're training your data, or when you're reading training data or writing checkpoints. And then for the broader set of workloads that might still need a file interface, but we don't necessarily offer a dedicated software package, we launched Mount Point for Amazon S3. If you're not familiar with Mount Point for Amazon S3, it's a file client that provides local file system API calls to S3 objects. This allows you to do simple reads and writes with a file interface to your S3 data lake. Now, it's not a file system. It doesn't provide the locking capabilities of shared storage. It doesn't provide capabilities like renaming a file. But for many workloads, this provides a very simple way to have scalable access with a file interface to your S3 data lake. I mentioned before that Amazon S3 provides high levels of throughput. The Mount Point connector actually provides an optimum data transfer by looking at the specific instance that you're using to run your workload and spinning up the right number of parallel threads to drive that I/O from S3 to your compute instances in parallel without having to do anything on your end. So it takes care of a lot of the heavy lifting to get the best performance possible out of Amazon S3. And then we've also added capabilities like data caching. Sometimes that 10 milliseconds that I mentioned before isn't quite sufficient to keep up with all of your low latency workloads. This is where something like caching the data that you've already read on the local instance on EBS or local NVMEs can be really helpful in improving performance for subsequent access. So we've talked a little bit about what types of storage and storage requirements our customers have when they're working with existing foundation models. And for many of you, that's going to be the end of your journey. But we also wanted to make sure that you knew that for anyone who is going to be training their own model, we have the storage needs to support those workloads as well. What we hear from customers who are training their own models is they're looking for broad compatibility with ML libraries, they're looking for scalable performance and low latencies, and they're looking for an intuitive, collaborative environment. Now, training a model from scratch is very different than working with an existing model. Oftentimes, when you're training a model from scratch, you need to access many different libraries that are specific to your domain or the approach that you're taking to train. you might need tools like deep speed to break up your data so you can perform data parallelism and distribute that data across the multiple GPU nodes in your cluster. You might want to take advantage of something like Megatron LM to split up your model and, again, distribute it across the GPU nodes in your cluster for training purposes. And then you also might take advantage of something like NeMo if you're working with speech recognition. So all of these specialized libraries that are out there are all accessible to you if you have broad compatibility and the ability to run these libraries and build on them when training your workloads. These are also all accessible within Amazon SageMaker HyperPod. HyperPod allows you to take advantage of the fully managed GPU capabilities of SageMaker, so to keep those GPUs stable, running, and have all the efficient logging that's available in SageMaker, while also giving you SSH access to run whatever libraries you want on the actual nodes. The next thing that customers have asked us for is scalable performance and ultra-low latencies. We've talked a bit about this idea that you need to take the data from your storage and feed it into your training instances, that you might need to save the state of your model back to storage at intermediate states in case there's a node failure during the training process, or to restore the model to a previous state and time later so you can reevaluate its accuracy before and after certain changes that you've made in your training process. Now, this is important for a number of reasons. One of them is that we've been seeing the training throughput requirements of our customers increasing over time. We've talked a lot about text-based models, which are really dominating a lot of the discussions here at reInvent. Text-based models, what we see in general is that they require about 128 megabytes per second of throughput for each GPU that's being used to train the model. As you start to look at more multimodal models or video-based models, the throughput requirements of your storage increase. And you can imagine if you've got 2 gigabytes per second of throughput that you're trying to feed to a GPU instance, and you've got 100 GPUs, the throughput requirements of your storage start to add up quickly. I mentioned latencies earlier and how those can be important to make sure that you're optimizing your GPU workloads as well. Just as a refresher on latencies, every time that you make a request to read data from a storage service, there's overhead for authentication and authorization, overhead for metadata lookups to actually figure out exactly which disk is storing the data you're looking for. And then there's the just sheer round-trip latency of the networking itself. Now, overall, this overhead shouldn't be a problem unless the amount of data that you're requesting with each request is also relatively small. And so if you're working with a lot of small files, which is something that we've seen particularly in generative AI applications for drug discovery, working with ZAR files, you're going to want to make sure that you're working with a low latency storage layer so that as these requests add up, you're able to minimize the training time and the overhead cost of each of these round trips for the I/O. The last thing that we've heard from our customers is that training a model is an inherently collaborative experience. You've got domain experts, ML ops folks, cloud architects, everyone working together, oftentimes many researchers in a specific domain. And what they're looking for is a familiar interface, POSIX permissions, consistent data access that protects them from overwriting each other, while still benefiting from a lot of the capabilities that they get in the cloud. And so to actually train new models, what we're seeing is customers are turning to Amazon FSx for Lustre. Now, if you're not familiar with Lustre, it's the world's most popular high-performance file system. It's used by national labs and world's leading ML researchers. It is a file system, just like any other, so you can mount it on a compute node and share data, read and write. It supports POSIX permissions, prevents customers from overwriting each other's content, and is an intuitive way to work in a collaborative environment while still achieving high levels of performance. We mentioned some of the performance requirements with video training. FSx for Lustre can support up to hundreds of gigabytes per second of throughput, millions of I/O per second for those ZAR files as an example. And it supports consistent sub-millisecond latencies. Again, great for small I/O. This week, we actually launched a new capability to improve the performance that we can drive between our file systems and a single GPU instance with the support for Elastic Fabric Adapter and GPU Direct Storage. So we now have the fastest storage in the cloud for GPU instances. In this case, we can actually read or write data between a Lustre file system directly into GPU memory, bypassing all the memory copies and the CPU to actually minimize the CPU load on those GPU instances, reduce latencies, and optimize throughput. So if you're trying to keep your GPUs busy, especially in a context where they're very I/O hungry, this is going to be a great capability to have in your arsenal. And so that gives us 150 gigabytes per second of throughput for each client instance. The last thing I want to call out with FSx for Lustre is its capabilities while working with an Amazon S3 data lake. So you can take your Amazon S3 data lake and connect it to an FSx for Lustre file system. You can put your objects in S3 and transparently represent the file or the objects that you have in your data lake on your file system without actually moving any of the data. Then, as your EC2 instances request content, FSx can go fetch that data in real time, or you can choose to preload it on the file system if you want to optimize latencies. As you add data to your S3 bucket, you can choose again to automatically synchronize with your file system so that the metadata is visible again. And if you write data to your file system, you can choose to have that data be automatically sent back to Amazon S3 and synchronize your data with your S3 bucket. What we found is that this provides a nice best of both worlds experience for a lot of our users. They're looking for something that provides that intuitive, collaborative environment of a file system for interactive research, while still providing storage and IT administrators with the ability to manage their data in the way that Bijat had mentioned before, take their pipelines of data, keep them up to date, govern and audit all their transactions, and make it really easy for storage administrators to share data as well across organizations and teams. A great example of a customer who's taking this best of both worlds approach is Adobe. Similar to LGAI Research, they use both Amazon FSx for Lustre and Amazon S3. In this case, they use FSx for Lustre to try out and experiment a number of different models with researchers and domain experts. And then as they find interesting models that might be useful to their customers, they refine them, and eventually they put them into production training on Amazon S3 and deploy them through their S3 data lakes. So it's a great way for them to both get the best of a file system like FSx for Lustre, while also a data lake like Amazon S3. So to recap, we talked about selecting an approach, we talked about creating a data plan, and creating a storage plan. When you're selecting an approach, RAG is ideal if you're going to try to take an existing model and give it access to your own external data sets without building them into the model itself. Gives you the ability to have highly accurate results because you're going all the way down to the source of the information rather than allowing the model to interpret and come up with its own response on its own. We talked about fine-tuning and how you can label data and teach an existing model how to do a specialized task and some of the process that's involved in preparing that data as well. And then for continued pre-training or training your own model from scratch, we talked a little bit about how that allows you to really get accurate results on an existing model, or if an existing model doesn't exist, to make sure you have something to meet your needs. In data discovery, we talked about different options for places that you can secure data, whether that's your own organization, public or academic data sets, or by licensing data from third parties. All of these are options that we see our customers taking advantage of today. We also talked about how just because you have the data doesn't mean it's ready and optimized to be used in a generative AI application. Things like RAG workloads need you to pre-process and make sure that data is ready to be identified by the RAG workload in real time. That means tokenizing, chunking, and storing that data into a vector database so it can be easily matched as the users are working and generating prompts with their application. And then obviously for labeling, if you're doing fine-tuning, preparing that data so it's in a labeled structure to teach the model a specialized task is critical to the accuracy of the output. On the security and governance side, we talked about some of the tools that we offer, whether it's IAM permissions or lifecycle management to make sure that you adhere to any kind of government or licensed policies around your data. And then finally, we talked about creating a storage plan and how if you're going to be building on an existing foundation model, Amazon S3 gives you the cost-effective storage for both hot and cold data sets, how you might want to use some of the millisecond or tens of millisecond range S3 storage classes for RAG-based workloads, but how you can take advantage of the full spectrum of storage classes if you're going to be training and then moving that data into a colder tier. We talked about how Amazon S3 provides highly scalable performance for data retrieval and processing, and how it integrates with most of the key AI/ML workflows that you might need to run to build your applications. And of course, in areas where an object store isn't fully compatible, Mount Point can help close many of those gaps. And then if you are building a foundation model from scratch, we talked about how you can use Amazon FSx for Lustre to get access to virtually any ML library that's out there, which might be helpful to fully optimize those GPU resources. We talked about how it provides tens of gigabytes of throughput to GPU instances, hundreds of gigabytes per second of throughput in aggregate, and an intuitive environment for collaboration, including the ability to connect with an Amazon S3 bucket and synchronize data so that you can provide your users with a collaborative environment while still storing your data in an Amazon S3 data lake. If you're looking to learn more, a couple sessions that we've picked out here. We've got a session on using Amazon SageMaker Hyperpod, which is specifically used for training Gen AI workloads. There's another session around using Amazon Bedrock, similar to the demo that you saw earlier, if you're going to be building on an existing foundation model. And then we've got a couple of particular sessions that we recommend to get the best performance out of your storage across object and file workloads as well. So with that, we'll call the session an end. And if you have any questions, Bajeta and I will be up at the front, and we'll hang around for a few minutes. Thank you so much.